Hello everyone, welcome back to this online class. Today we are going to look at how to solve non-homogeneous linear ODEs of the second order, and in particular we are going to look at the method of inverse differential operators. Now we are given this example. We are asked to solve the following differential equations. In part A, we have d squared y over dx squared minus 6 dy over dx plus 9y is equals to 6 exponential 3x. In part B, we have d squared y over dx squared plus 9y is equals to 18 times cosine of 3x, subject to the initial conditions that y is equals to 0 when x is equals to 0, and y prime is equals to negative 6 when x is equals to 0. So let's see how to solve those two problems. Now, first of all, we need to write them in terms of the d operator. Let's define our d operator. So you're going to say let d be derivative with respect to x, so that where we have d squared, that will be the second derivative with respect to x twice. Now, in part A, we need to write in terms of the d operator. So remember, we are solving this. In terms of the d operator, what will it look like? It will now be d squared minus 6d plus 9, everything operating on y to give us 6 exponential 3x. So I'll write here that d squared minus 6d plus 9 operating on y to give us 6 exponential 3x. So this is a non-homogeneous ODE. It has two solutions. The first one is the complementary function, which we denote by y subscript c of x. So how do we get it? We need to solve the homogeneous part. Let's call this star. So you solve the homogeneous part of that equation star. That is d squared minus 6d plus 9 operating on y to give us 0. So what is the auxiliary equation? We can write here auxiliary equation. You simply equate the coefficient of y to 0. So that is d squared minus 6d plus 9 is equals to 0. This is quadratic in the d operator. We can now find the roots. Remember, this thing here can be factorized to take the form d minus 3 squared is equals to 0. So what are the roots? The first root is equals to the second root, and so the result is 3. 3 is a real number, so this is a case of real and equal roots. The roots are real and equal. So how do we write our general solution? So you can just say that therefore y subscript c of x, a function of x I mean, is equals to a constant c1 x plus another constant c2. The whole of this is multiplying exponential 3x, where c1 and c2 are arbitrary constants. So that's the first solution. Let's find the second solution. That is what we call the particular integral. This is denoted by y subscript p as a function of x. So using the inverse d operators method, what we do is make y the subject in equation star. Look at our equation star. We need to make y the subject, so this is equals to I'm going to divide by the coefficient of y. So this 1 over d squared minus 6d plus 9 operating on 6 exponential 3x. If you look at case 1, we said where there is d, you need to replace by alpha. In this case, alpha is 3. If I replace d by 3, we'll have 3 squared minus 6 times 3 plus 9. That will give us 0. Take note here. You write a note that case 1 fails. Case 1 fails. Why are we saying fails? Because since 3 squared minus 6 times 3 plus 9 is equals to 0. There's a division by 0 in the denominator, and so case 1 will fail. So we cannot use case 1. What we do is to use the exponential shift rule. So in such case where case 1 fails, you now need to use exponential shift rule. Remember, you cannot divide by 0. That's why we are saying this case 1 fails, because in the denominator there will be a 0, and it is not possible to divide by 0. Division by 0 is not possible. So what do? We need to shift exponential 3x to the left of the inverse d operator. Take it here. In this case, our alpha is equals to 3. So when you shift to the left, where there is d, you are going to use to replace it by d plus alpha. So that means d plus 3 because our alpha is 3. So what we do here is, I can write here, replace d by d plus 3 because our alpha is 3. So this will now be equal to exponential 3x times 1 over d plus 3 squared minus 6 into d plus 3 plus 9. Now we remain with 6. So let me work out the denominator. So you can say d plus 3 squared minus 6 into d plus 3 plus 9. What is it equal to? It is the same as d squared plus 6d plus 9 minus 6d minus 18 plus 9. And so this, when you simplify, you get d squared. You can see 6d and the other one will cancel, 9 and 9. So we simply get d squared. Because the rest will cancel. This will cancel with this. 9 plus 9 is 18. Will cancel with the other negative 18. So that this can now be written as exponential negative 3x 1 over d squared operating on 6. And you see 1 over d squared is the same as writing exponential. Was it negative 3? No, it was positive 3. So change it. Exponential 3x d raised to negative 2 operating on 6. This means the integral operator integrates 6 twice with respect to x from 0 to x. So you can take note that d raised to negative 2 is simply the double integral 0 to x, 0 to x of whatever you have there with respect to x. Integrate whatever you have there twice. So this is what you're going to get. Is the same as exponential 3x d raised to negative 1 of another d raised to negative 1 of 6. And so this should give you exponential 3x d raised to negative 1 of 6x. When I integrate 6, I get 6x. And again, when you integrate further, you get exponential negative 3. No, that's positive 3x. Integrate 6x from 0 to x, that will give you 3x squared. So that what we have here is 3x squared exponential 3x. So that's our particular integral. What I want you to take note that when case 1 fails, use the exponential shift rule. Just like we have done it there, exponential shift rule will be applied in almost 3/4 of what you do in second order ODE. So we need to get our general solution. What you do is to add the two solutions together. So you can write that general solution is equals to the complementary function plus the particular integral. So what was our complementary function? You say, or y is equals to yc plus yp. Or I can replace them. Y is equals to c1x plus c2 exponential 3x plus the other one we have found 3x squared exponential 3x, where c1 and c2 are arbitrary constants. So this is our general solution. If you are given some initial conditions to apply, those will help you find the values of the arbitrary constants c1 and c2. Now let's solve part B. I'll write here part B. Again, we need to write that in terms of the D operator. Let's go back to the question in part B and write it in terms of the D operator. This is the question. When you write in terms of D operator, we'll have D squared plus 9 operating on y to give us 18 cos 3x. And there are some initial conditions that y of 0 is 0 and y prime of 0 is negative 6. So first of all, let's get our general solution, and then we'll apply the initial conditions to get the particular solution. So we go back to part B here and write it in terms of the D operator. We'll have D squared plus 9 operating on y to give us 18 cos 3x. We have two solutions. The first one is the complementary function, which we denote by yc of x. And how do we get it? You need to solve the homogeneous part of that equation. That's d squared plus 9 operating on y to give us 0. Remember, we are solving the homogeneous part of this equation. We call it equation star. So what is the auxiliary equation? Is d squared, let me use another color. Auxiliary equation is d squared plus 9 is equals to 0. We can find the roots, and that is d 1 and 2 is the square root of negative 9. And so that is 0 plus or minus iota times 3. So that alpha is 0 and beta is 3. So when you have such kind of roots, these are complex conjugate. The roots are complex conjugates. How do you write your solution when the roots are complex conjugates? it will be yc of x is equals to exponential 0x c1 cos 3x plus c2 sine 3x. And you know, anything raised to 0 is 1. So this is the same as c1 cos 3x plus c2 sine 3x. You can just say or yc of x, where c1 and c2 are arbitrary constants. So that's our complementary function. Let's find the particular integral, the second solution. Particular integral that is denoted by y subscript p. You can use another color. That is y subscript p of x. How do we get it? Make y the subject, so you divide through by the coefficient of y in equation star star. So that will be 1 over d squared plus 9 operating on 18 cosine of 3x. Now look at the coefficient of x here. This is alpha. Alpha is -3. So alpha squared will be 9. Alpha is 3, sorry. Alpha squared will be 9. And so negative of alpha squared is -9. When you replace d squared by negative of alpha squared, that will be -9 here plus 9, which is 0. Remember case 2. Case 2 will fail. Case 2 fails. So you can take note that case 2 fails. Why? Since d squared plus 9 is simply equal to -9 plus 9, which is equals to 0. Remember, we said d squared is equals to negative of alpha squared. That's what we said in case 2. That where this d squared, you put negative alpha squared. And in this case, our alpha is 3. So when we do the substitution, we get 0 in the denominator, which is not possible. It is not possible to divide by 0. And that's why we are saying case 2 fails. So in such case, if it fails, you use the exponential shift rule. Use exponential shift rule. Now, what do we do? You see, you only shift an exponential function, but here we don't have exponential function. So first of all, I need to introduce the exponential function. How else can you write cosine of 3x in terms of exponential function? I want us to take note of the Euler's identity. Take note of what is called the Euler's identity, that where we have exponential 3x, of course this iota times 3x is the same as that would be the same as cosine of so that is cosine of 3x plus I sine 3x. So I'll write here cosine 3x plus I sine 3x. That's what is called the Euler's identity. If you replace 3x by theta, it will be exponential I theta is equals to cos theta plus I sine theta. I is the square root of -1. It's called the iota. I is equals to the square root of -1. It's a Greek symbol that is called iota. So that's what I'm going to do. Instead of exponential 3x, instead of cosine 3x, I'm going to replace it by exponential I3x. And you see, cos 3x is the real part. This is the real part of that complex number. So this is the real part. This other one is the imaginary part. So you realize that for me to get cos 3x from this complex number, I simply need to extract the real part of that complex number. So we can say that therefore, yp of x is equals to the real part written as Re of this one now, 1 over d squared plus 9 operating on 18 exponential I3x. So you work out it and then you extract the real part of whatever result that you shall have found. So let me work out what is in the bracket. And once we are through with it, then we extract the real part. So here we use shift rule. So we take note that 1 over d squared plus 9, 18 exponential I3x is equals to, if I shift it to the left of the inverse D operator, of course I'm shifting this one here, it will be exponential I3x. When you shift, what is our alpha? The coefficient of x is iota 3, iota times 3. That's our alpha. So replace d by d plus alpha. So where we have d, it will be d plus alpha, which is iota 3, and this is squared. Then I can see plus 9. What we remain with here is 18. 18 is a constant or a polynomial of degree 0. So this is equals to, if I open the bracket in the denominator, that will be exponential I3x 1 over, that's d squared plus I squared times 6d plus 9. Not 9. Let me just rewrite that. It's not I squared here. It is I times 6d, then plus I squared times 9. Then I can see plus 9 operating on 18. But we have said I is the square root of -1. So what is I squared? So you can say, but I squared should be equal to -1. So that means that this one and this will cancel because I squared is -1. So it's like we have -9 plus 9 that will cancel out. So what we remain with is this one, exponential I3x 1 over, I can see d is common, so we have d outside. Then we have d plus I6 operating on 18. So what do? I need to get rid of the complex number in the denominator. So this can as well be written as exponential I3x 1 over d plus I6, then times d inverse of 18. The other d, 1 over d is the same as d inverse. I've written this as d inverse And I tell you D inverse is the same as integrating. So when you integrate 18 with respect to x, you get 18x. So that this can be written as exponential I3x. Then here we have 1 over D plus I6. There we'll have 18x. 18x. So what do we do? You need to use Maclaurin series expansion, or you could get rid of the complex number from the denominator. That's easier. There are two ways. Just use whichever is easier for you. So this can be written as exponential I3x. Then here we have 1 over, that will now be D plus I6 times D minus I6. Even the numerator you should multiply by D minus I6. So let me rub this and replace it by D minus I6 in the numerator. So here we have D minus I6. Here we have 18x. So if I continue simplifying this one, what will we have? It will be exponential I3x D minus I6 in the numerator. Denominator is difference of two squares, that is D squared minus I squared, that is I squared times 6 squared, that is 36. Then here we have 18x, but I squared is -1, so this can be written as exponential I3x D minus I6 over D squared plus 36, operating on 18x. 18x is a polynomial of degree 1. So you can comment on this and write this as, say this is a polynomial of degree 1. Polynomial of degree 1. And look at D squared. 2 is greater than 1. So we are going to drop the term containing D squared. Why? Since 2 is greater than the degree of the polynomial, which is 1. So I'm going to drop this so that what I have is now 1 over 36 exponential I3x times D minus I6 operating on 18x. And now we can open the bracket. Let's open it. This is still the same as, I can write it here, 1 over 36 exponential iota times 3x. Now, inside that bracket, it means derivative of 18x. That is, let me write in full, derivative of 18x minus I6 times 18x. That's what it means. And so this is the same as 1 over 36 exponential I3x. Here we'll have, when you differentiate 18x, you get 18. Then minus, now work out I times 6 times 18x. So what are we going to get? We just multiply 18 times 6, that is 108. So that's negative I times 108x. But you also need to replace the exponential I3x. So we need to go back to the Euler's identity so that we replace exponential I3x. Let's check where we defined it, Euler's identity. Where we have exponential I3x, that is the same as cosine of 3x plus I sine of 3x. So that's what I'll write here. Let me replace it. So this is equals to 1 over 36. Here we have cosine of 3x plus I sine of 3x. Then here we have times 18 minus I times 108x. So if I group it into real and imaginary parts, this is the same as 1 over 36. Let's start with the real parts. I'm opening the bracket. Cos 3x times 18, that is 18 cos 3x. Then the other one, if I take this times this one, I'll have I squared. I squared, remember? Okay, let me just multiply everything. Cos 3x times 18, then minus I 108x times cos 3x, then plus I 18 sine 3x minus I squared 108x sine 3x. I've multiplied those two brackets. And remember, I squared is -1, but I squared is -1. You can take note of that. So where we have I squared, we are going to replace that by -1. So these are not. So this can as well be written as 1 over 36, 18 cos 3x. So I replace I squared here by -1. That will now give us plus 108x sine 3x. So that's the imaginary part, not the imaginary, but the real part. Then plus the other part is 1 over 36, the part containing I. Then we start with this. Let me start with 18 sine 3x. 18 sine 3x. The other one is minus 108x cos 3x. So we said our yp of x is the real part of this result that we have found here. Let me just comment here and say this is the real part of our solution. This other side is the imaginary part. Imaginary part. So you can say, therefore, yp of x is equals to the real part of the solution. Real part of that result. And so that is equals to 1 over 36 into 18 cos 3x plus 108x sine 3x. And you see 18 is common. That can be factored out so that we simplify this result. 18 is common, so this can be written as 18 over 36. So that here we have cosine of 3x plus 6x sine of 3x. And 18 over 36, that is simply 1 over 2. So this is the same as 1 over 2 times cosine of 3x plus 3x sine of 3x. So that's our particular integral. And now we can get our general solution. General solution is equals to complementary function plus the particular integral, or y is equals to yc plus yp, or let me replace them. Y is equals to, what was our yc? You can go back and check. The complementary function, that was c1 cos 3x plus c2 sine 3x. So I'll go back here and replace it. C1 cos 3x plus C2 sine 3x. Then the particular integral we have found 1 over 2 cos 3x plus 3x sine 3x, where C1 and C2 are arbitrary constants. So this is the general solution. Now we have initial conditions to apply so that we get the values of C1 and C2. And so the resulting solution will be the particular solution. So apply the initial conditions, apply, that should be apply. The initial conditions. The first condition is y0, y of 0 is equals to 0. This means that when x is 0, comma, y is also equal to 0. So let's apply this condition into our general solution. We are going to get 0 as the solution is equals to C1 cos 0 plus C2 sine 0 plus 1 over 2 cos 0 plus 3 times 0 sine 0. So where we have sine 0, those will vanish. This is 0. And cosine of 0 is 1. So take note that where we have cosine of 0, the result should be 1. Cosine of 0 is 1. So this means that we have, or 0 is equals to C1 plus 1 over 2. So therefore, what is our C1? So this means that our C1 is equals to negative 1 over 2. So I now replace it into the general solution, and so you say therefore y is equals to negative 1 over 2 cos 3x plus C2 sine 3x plus 1 over 2 cos 3x plus 3x sine 3x. That's what we have. And we can simplify this one. You see, this and this will cancel. So you can say or y is equals to C2 sine 3x plus 3x sine 3x, which you can write as y is equals to C2 plus 3x. This is multiplying sine 3x. So I also need to apply the other condition. Y prime of 0 is -6. Before we apply, let's differentiate this, because the other condition is the derivative condition. So this means that our y prime is equals to, use product rule, there will be differentiate u, that is 3 sine 3x plus 3 into C2 plus 3x cos 3x. That's what we have when you differentiate it. Remember, use product rule. U prime v plus u v prime. So we need to apply this other condition. Y prime of 0 is equals to -6. So what does it mean here? That when x is 0, y is negative. Y prime, I mean, not y. So you can write here that when x is equals to 0, comma, y prime should be equal to -6. So again, let's apply it. Let's see what you're going to get. It will be -6 is equals to 3 cos 0, 3 cos 0 plus 3 times C2 plus 3 times 0, that is just 0. Let me write in a better way. X is 0, so 3 times x, that is 0. Then here we have cos 0. Remember here it was sine. Don't make those very little mistakes. So this is sine of 0. Where we have sine of 0, the result is 0. So this will vanish. Cosine of 0 is 1. So this simply means that -6 is equals to 3 times C2. 3 times C2. And so from here, it means that our C2 is equals to -2. So therefore, our particular solution I now replace it back here where we have C2. So that means we'll have y is equals to 3x minus 2 times sine of 3x. So that's the particular solution of the given problem in part B. So you see, for you to get particular solution, first of all, you must be able to find the general solution where you add the complementary function and the particular integral, and then you apply the given initial conditions to find your particular solution. So this is how to use the inverse D operators to solve non-homogeneous ODEs of the second order. And we have illustrated the concept of the exponential shift rule. Thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving inverse differential operators method. Bye-bye.